Hey, we're going to look at the brightnesses of stars and the magnitude scale in this video. And measuring the brightnesses of stars, something called photometry, is something that was first done back in ancient times. And it was a guy by the name of Hipparchus who developed the magnitude scale and invented it around, he lived around 150 BC. He was a Greek astronomer, and he was able to distinguish 6 different levels of brightness among the stars in the sky. And so he numbered these with 1 being the brightest and 6 being the dimmest. And so we speak of the brightest stars as being stars of the first magnitude, and stars that are dimmer being second or third or fourth or fifth or sixth magnitude. And the dimmest stars that he could see with his naked eye were sixth magnitude stars. He could just barely make those out. And he cataloged a lot of stars this way, around 1,000 stars. He had the advantage of there was no light pollution back then or air pollution, and he was a really good observer, but he had no telescope, and it's really hard to measure these things very exactly when you're just eyeballing them. And at that time, he had no mathematical basis for his scale. So now we look at stars like this, and you can see that they have different brightnesses, right? And we have now put on a mathematical basis for the star magnitude system. So what the people decided was that a difference of 5 magnitudes would be 100 times brighter. So a 1 magnitude difference is about 2.5 times brighter. Now, the downside of this scale is that the brighter stars have a lower number, and the dimmer stars have a higher number. And usually, when you measure something, the one that has more of it has a higher number, not a lower number. So it's kind of a little bit of a backwards scale, but it makes sense, I guess. So when we look at some of the stars now, having formalized this thing, we can say that the brightest stars, like Sirius, Sirius would have a magnitude of negative 1.6. So when we actually came up with a mathematical basis and actually used photometers, electronic equipment, to measure the brightnesses, it turned out that some of the first magnitude stars were even brighter than that. And so we've been able to extend this even to negative numbers. So even really bright things could have negative magnitudes, whereas very dim things will have magnitudes up around, 19, 20, 21, somewhere around there. So we can extend it in both directions. So Sirius, that's the brightest star in the sky, and it's magnitude minus 1.6. And there are other stars you could measure the brightness of, like Bellatrix. Bellatrix. She's my favorite Death Eater, but this is the actual Bellatrix, the star, which comes in at a magnitude of 1.6. So that's another bright star up there in the sky. And we've been able to extend this to other objects too, other than stars, although the sun is a star. So technically, the sun is the brightest star in the sky at a magnitude of negative 26.2. But the full moon comes out at a magnitude of about minus 12, which is pretty bright. And Venus. Venus, the planet Venus, comes in at a maximum magnitude of about minus 4.4 when it's really shining bright. And now, the magnitude is actually only the apparent magnitude, the apparent brightness. And that's because the magnitude depends on a couple of different things. One is the luminosity of the star, and that is how actually bright it is. And so for that, we usually just compare it to the sun. We give the sun a luminosity of 1 L sun, or 1 times the luminosity of the sun. So some stars are intrinsically brighter, and that's important in determining what their magnitude turns out to be, their apparent magnitude. And then another thing that affects them, so Sirius, if we looked at Sirius, its luminosity is 23 times the luminosity of the sun. So it is actually literally 23 times brighter than the sun. But the problem is it's much farther away, right? We're very close to our sun, but Sirius, the star, the dog star, is very far away from us. And so it looks dimmer. So that's the other thing that makes a difference is the distance. So as you get farther and farther away from something, the brightness drops off. And it drops off actually as the square of the distance. So that if you increase the distance from 1 to 2, the brightness drops from 1 to 1/4. 1 over 2 squared. And if you triple it to 3 times the distance, it'll drop to 1/9, 1 over 3 squared. And so the distance actually makes a bigger difference in how bright the star really appears. There's a equation you can use for this. The brightness is equal to the luminosity divided by 4 pi times the distance squared. So we have the apparent magnitude, and that's the brightness measured at its actual distance from Earth. But then we can also choose to look at something called the absolute magnitude, which says, let's imagine that that star was not at its actual distance, but was at a standard distance of 10 parsecs. 10 parsecs is actually about 32.6 light years away. And that's far enough away that it would look like a regular star, and a nice round number of 10 parsecs. So at that distance, the sun, for example, would be about almost a fifth magnitude star. It would be a magnitude of 4.6. So our star is not particularly that bright. Sirius would be about a 1.3 magnitude star, so still a pretty bright star at that distance. But Rigel, it turns out, would be a really bright star. It's about 20,000 times brighter than the sun, and it would have an absolute magnitude at 10 parsecs of minus 6.2. So it would be way brighter than any star in the sky right now if it were at that standard distance of 10 parsecs.